We are now going to go to where you have two separate reactions, right? Sometimes you have a first reaction where something is in excess, and then they do a titration to determine what is in excess. So let's just look at the planning of this one. I think our time is going to run out. We won't be able to do it, but let's just look at the planning. They say X gram of magnesium reacts with 200 cube centimeters of 0.15 moles per cube decimeter HCl solution. They give us this. And what's the important thing? They're telling us the acid is in excess. And that is a problem, right? May you work with that excess. Now, you may never work with the excess, right? Because that means you're going to get to bigger answers. Some of that will be lying on the table. So what I find the best way to do this is the moment that they tell you something is in excess, go to that substance that is in excess and draw a little table for yourself. It's sort of like the rice table, you know, that KC value table, right? It's what do I start with? How much react, because it's the amount that react that is going to determine how much of this react. And then what is the excess? Right, so they tell you that it reacts and the acid is in excess. So there's something left over. And now the acid that is in excess is titrated with sodium hydroxide and they tell you 25 cube centimeters is used to neutralize this. Right, so whatever is left over there is being used in a second reaction. So now you say, okay, for the second reaction, they give you the volume and the concentration of the NOH. That you can use to get the moles. Grade 10, easy. Right, moles to moles is a ratio. Easy, right. The grade 12 thing is to remember that whatever moles react here is the moles that was left over there. So once you get this moles, just go and write it down there as well. And then you say, okay, they told me what I'm starting with up there. Up there they told us the C and the V of the HCl in the beginning. So you can do the mole calculation and work out how many moles did we put in. And then you can subtract them to see how much reacted. They put in, calculation, they put in 0.03. You do this and you find out in the second reaction you had 0.02 of the HCl, so there was 0.02 left over. So how much reacted? Substitute, 0.0, subtract 0.02, 0.01. That's what reacted. So it will tell you how much of this reacted, which would give you the mass. Are you all right? So actually, I hoped that we will have time. There's at least 10 minutes, so we can see if we can make it. Right, for you to do one. So on the next page, let's see if you can do this in 10 minutes. If you can at least do your planning, so write down the two equations, draw a little box for the one that is in excess, and do the planning of how you would do the question, even if you can't do all the calculations, right? So do the planning. Right. So let's read slowly, and we do at least the planning so you can see where we're going. They say a learner adds a sample of calcium carbonate to hydrochloric acid. And they're nice, they give us the equation. So let's start by writing the equation. So we can write down what they give us and what we're looking for. Right, so I have my equation. Now they say a learner adds a sample of calcium carbonate to 50 cube centimeters of hydrochloric acid of concentration 0.1. And here they give me the trick. The hydrochloric is in excess. So at this moment, to make it easier for yourself, go to the hydrochloric acid and draw a little table. Because you are going to put some moles of HCl in, and some of that moles will react, and some of that moles will be left over. Everyone happy up to there? Okay, let's read the rest. Now they say this excess, what is left over, is now neutralized by 28 cube centimeters of 0.5 sodium hydroxide. So let's take the second one. HCl plus NaOH is NaCl plus H2O. Right. So there's my second reaction. So let's reread. The excess hydrochloric acid, it's that. It's whatever is left over, right, is neutralized in the second reaction. So they use this in a second reaction. So what's left over is straightforward used in the second reaction. And what in the second reaction, this is neutralized. What can we say for neutralized? They will be in the right ratio. Right, they are in the right ratio. And now they give you sodium hydroxide. They give you a volume of 28,0 cube centimeters, and they give you concentration 0.5 moles per cube decimeter. Right. And what do they ask you? They ask you what mass of calcium carbonate, this one, was in the sample. What reacted? Right. Now, if I'm going to this moles of calcium carbonate, I want to end up with mass of calcium carbonate. Right, that's where I'm working towards. But to get mass, I need moles. Do I get that moles from what I put in HCl? No, because not everything of that HCl is going to react. That's more than enough. That's excess, right? So I can't work with that. Some of that will be left over. I should work with what? React. Because the HCl that react will tell me how much calcium carbonate reacted. All right? So that's where the mole ratio is. React with react. So the very first thing is we're going to start with this one and work out how many moles of sodium hydroxide was used in this neutralization. That will tell me how much moles of HCl was neutralized. Better. Right, can I try and make it even more bigger? Right. Okay, so we're going to start over here and we were going to work out how many moles of sodium in this second reaction. So always think about it. It's what's happened in the second, what's happened in the first. Right. Now we're going to start with the second reaction. And we're going to say concentration is mole per volume. I'm working with the NaOH. Right. The concentration 0.5. Volume, just watch out, that was cube centimeters. How do I go to cube decimeters? Divide by 1,000. So that will be 0.028. So then I get the moles is 0.014 moles of NaOH. I'm over here. I know how many moles of base was used in the titration. Okay, but I know they in the second reaction, the HCl to NaOH, they react 1 to 1. So if 0.014 of that reacted, it tells me 0.014 HCl reacted in the second one. So we've now, up to now, only worked with the second reaction. But what do we know? If that was what reacted in the second one, that was what actually was left over in the first one. So 0.014 HCl was left over in the first reaction. So now we have that one. Okay. Now, let's go back to the first reaction now. We've got that one. We are now back with the first reaction. What did they tell us about the first reaction? They told us actually that the HCl was 50 cube centimeters and it had a concentration of 1 mole per cube decimeters. Right, that was what I put in in the first line. They said the learner added a sample of calcium carbonate 2. So this was what they put in. So now we're working with the first one. And we're going to say, what did I put in? The HCl that I put in, C equals N over V. Concentration that I put in was 1. Volume that I put in, 50 cubed centimeters, decimeters. How do I get it? Divide by 1,000, 0.05. So how many moles did I put in? 0.05 moles of HCl. That was what I put in up there. Right. So that's what I put in. How do I get what I used? I'm going to take what I started with, what I put in, and subtract what was left over. Right. Right, so the HCl that reacted was the 0.05 with which we started, minus the 0.014 that is left over. And that should give you 0.036 moles. Right, and this is what reacted. So if you look at this, we're now up to what reacted. And what reacted of this one will tell me what reacted of that one. So we're now doing this. We're saying, okay, so go from calcium carbonate, HCl, is in the ratio 1 to 2. I now know of the HCl 0.036 moles reacted. So how many calcium carbonate reacted? Half of that, 0.018 moles of calcium carbonate reacted. Did they ask us moles? No, they asked mass. But okay, it's easy to go from moles to mass. Moles is mass divided by molar mass, 0.018. Remember, we're working with calcium carbonate, so you have to use 100, which is the molar mass of calcium carbonate, and then you get a mass of divided by times 100, 1,8 grams of calcium carbonate. Percentage yield and percentage purity. Now, if I look at percentage yield and percentage purity, they're different, and you really have to know which one is which. Now, let's look at percentage yield first. Percentage yield is what you produce. So with percentage yield, you will always have something like A, B giving you C, and with a mole calculation here, you are going to do a theoretical yield. You are going to work out what is possible. So on paper, what is possible? So you will have a mass that they give you, right? And that you will use to determine the moles. Moles will give you moles of that, and then you will know, and this is what is possible, right? So what you're going to do is you're going to do a mole calculation from left to right, because you are working out the possible yield. You can't work out the actual yield. They have to give it to you. You don't know if this guy is good in the lab or not. Then percentage purity, you are given something, a sample of something, and if you think about a sample, say for instance they tell you you've got a 20-gram sample of magnesium, but they tell you that it is unpure. Now if it's unpure, it means some of that in there is magnesium, but some of that, let's say it's junk, not necessarily junk, but something that reacts differently. Right, so you now want to know what is the percentage purity. So you have to know what is the real magnesium in the whole thing and what is possible. The whole sample is possible, right? The whole sample could have been pure. So that's why that one is at the bottom. And here you will have to do a calculation or something to determine the real magnesium. Now, how am I going to know what is real magnesium? Because I know what magnesium does. Magnesium, if I react that with HCl, That will give me magnesium chloride and hydrogen gas, right? And what I can do is I can measure that volume, right? And work back, and that will tell me how much magnesium was really in that sample, because only the real magnesium will be able to produce volume. So with percentage yield, you're going to work from left to right because you work out what is possible, right? While with percentage purity, you're going to work back because you did this experiment to determine how much magnesium was present, because only the magnesium could produce the product. So you're working back and then you're getting the actual, right? The real mass, right? So with percentage yield, you work from left to right and you work out the possible yield. With percentage purity, you do an experiment and then you have to work back to know how much magnesium reacted, and that will tell you how much magnesium was present. Right, let's move on to examples. The first one, they tell you in 21 grams of H2 reacts and produces 90. Now that 90, if they tell me it produced 90, it's not telling me that it was supposed to. It tells me the actual yield, right? So there you have actual yield. And then they ask us to do the percent, to calculate the percentage yield. Right, you can do this one and then come back and mark. Now, if you look at this one, N2 plus 3H2 to give you 2NH3, NH3. Right, they're telling you that of the hydrogen, there's a mass of 21 grams reacting. So what I will do is work out how much ammonia was possible, right? And then we can compare that with what we actually got. So how much was possible? Now first I'll say N equals M divided by M. The mass I have 21 grams, and that's for hydrogen, molar mass 2, and that will give you 10,5 moles of H2. Now I've done that. Right, now I'm going to go from one type of substance to another. And the moment you do that, you need a ratio, right? So we're going from H2 to NH3, and 3 of these will produce 2 moles of that. So I don't have 3, I have 10,5. So the question is how many moles of that? And when you do your cross calculation, that will tell you 7 moles of NH3 can be produced when that 21 grams react. Right, but we don't want moles, we want mass. So once again, N equals M over M. The moles now, that 7 is for ammonia. So the molar mass that I need is for ammonia, 14 and 3 giving you 17, and that will give you a mass of 119,00 grams of ammonia, right? And that was what was possible, right? I've worked from left to right and I've worked out what is possible. So now for the percentage yield, you have the actual yield divided by the possible yield, and that is times 100, right? Times 100. So here I will have the actual yield was 90, right? Out of a possible 119, and that tells me there's a 75.63 percentage yield. I only produced 90. I could have produced 119. Right, so that was one example of percentage yield, right? Moving to percentage purity. Remember with purity, you've got an impure sample. Remember, you can never ever use that 20 in a mole calculation because only part of that 20 is magnesium. So definitely never ever take the whole sample as your magnesium, right? So here we have to work back. Let's look at the next one. They tell you 12 grams of unpure copper immediately. That is your sample. Don't go using it in an equation, right? If it's unpure, only part of the 12 will be copper. And how do they determine what is copper? We are going to work back, right? They react according to the following equation and 2,24 cube decimeters of NO. So you have the volume there of 2,24 cube decimeters. That will give me the moles of NO. And then I'm going to work back to see from that mole to that mole, and then see what was the mass of the real copper in there. How much of that 12 was really copper? So I'm working out from right to left. So first I'm going to say N equals V over Vm because I'm working with a gas, right? So I've got my 2.24 divided by 22.4 because they told us we were at standard temperature and pressure, so that's fine, giving me 0,1 moles of NO, right? Now, from there to there, definitely a ratio. So I'm working from copper to NO, and that will be how many coppers? 3 to 2. And then also I'm looking for the copper, and I've got the NO, and that is now 0,1, right? And cross multiplication, and then I end up with 0,15 moles of copper, right? So I've moved to the copper. Now I have the moles. I want the mass. N equals mass over molar mass. The moles are for copper, and therefore the molar mass should also be for copper. And that gives you a mass of 9,53 grams of copper. So I've worked back, right? I've worked back, and I've worked out what is truly copper. Because of that 12 grams, only 9,5 reacted. And then I can say, okay, so the percentage purity will now be my mass of real copper divided by the mass of my sample times 100. So the mass of copper, real copper, 9,53. It could have been the whole sample of 12, and that is times 100 to give you 79,38%. And that was actually that they wanted us to prove that it is 79,38% pure. Remember, if you have to prove something, you cannot use that number. You have to get that number as your answer. Right.